Everybody, I'm pleased to introduce Achim Menges, one of our guests of our Miaw 2015. I'm very pleased to have here Achim. It's a pleasure to have him here. He's an architect and an expert, a professor in computational design. It's a very new and important discipline for architects, we think. That is why we are very pleased and we were very willing to invite him here, because it deals with innovative technology with a design approach. So it's not only technology, but it's a way to understand the design through new materials, new technologies, new tools. So the tools are not seen as simply a tool, but something that inform your design. So I think it's very important now, today, for you, for your practice, for your future. So that's why I thought that he was the perfect person now here. Thank you, Achim.
Thank you. Yep. Can you hear me? Yeah. Thanks for the introduction. It's a pleasure to be here shortly after lunch. I hope you had your espresso. I think we can keep it a bit sort of interactive, so if you have questions or ideas along the way, it's no problem to keep it a bit informal. Basically, what I'm going to try to show is it okay? I assume so, so I just rumble on, and when you start to fall off the chair, I stop. So the idea is basically to introduce you a little bit to the theoretical framework in which we operate, and then show you some more concrete examples, actually in depth, because only then I think the nature of the work is really revealed. So I think at the beginning, it's really important to maybe also understand what we mean when we refer to computation, because that may differ from sort of the conventional understanding, and I think it's also important because that's somehow an important aspect to the name of the institute. And I think when we talk about computation, we talk primarily about the processing of information. And I think this is important to understand because in that way, both sort of machinic processes that operate in the digital realm, as well as material processes that actually operate in the physical realm can be understood as computational. And while we all know that there's a strong bias towards what one can call machine computation in contemporary design, sporadic investigations of material computation have also occurred in architecture, and I will show a couple of examples of that. What has rarely been explored is the kind of overlap where machine and material computation meet, and where they not simply sort of coexist, but really intensely interact in the field of design research. So I think in this way, our kind of work and research really embraces a very particular contemporary condition of architecture, where one can probably argue that the separation between the process of design and the process of making is still very much intact. Actually, this separation, it has dominated design thinking since the Renaissance. But I think we are also becoming increasingly aware that things are beginning to quite dramatically change, and that we probably have the chance to reconsider or rediscover what the material is in architecture through the computational. Because these two worlds are no longer understood as separate, but computation actually becomes an intense interface for the physical world. And I think in this way, computation really enables us to engage aspects of the material world whose logics had previously remained ungraspable because they were basically lodged at too great a remove from the modalities of the designer's sense, intuition, and thinking. So I think in a way it's a relatively profound change. And it's a profound change that is interesting because it opens up the possibility to no longer conceive of material just as a passive receptor of predetermined form, but rather as an active generator of design. And I think that's also where it relates to the workshop that we're conducting as part of these 2 weeks. They can nicely see that this material system that we deal with, which is a pretty extreme example of Carola's research, has actually the capacity to compute form. And I think that the image on the left is an amazing evidence of that, which is a kind of photoelastic study. So this is not a digital simulation. It's actually looking at the actual load paths that the system recomputes every time you change something that is visualized through a special photographing technique. So every time the system basically has the ability or the intelligence to adapt to various configurations more or less by himself. Doesn't need to be pre-designed. And of course, I mean, this is not something that we came up with. This sort of more generative understanding of material as a kind of active design driver has actually quite interesting precedents. And I will just point at two, which are located in the kind of some of the most prominent academic ventures of the 20th century in Germany. So one could, for example, mention Josef Albers and his material studies that he conducted at the Bauhaus, actually, in Dessau, which really established a precedent for the possible enrichment of design processes through what Albers actually called material experimentation. So I think here it's really important to understand that these studies that you can nicely see here are not scalar models or representations of an idea. It's not a typical architectural model. It's really a kind of temporary unfolding of material behavior in space and time that becomes generative for you as a designer, and not just a representation of that. Possibly at the other end of the spectrum, one could look at Frei Otto's work that he did at the University of Stuttgart, where he investigated what he called form-finding methods that allowed him to study a vast number of different material systems to see how they have a capacity to physically compute form. Most famously, the soap bubble studies that he made, from which he actually sort of extracted the logics and forms for example, the Expo Pavilion of 1967. So we like to think of our work as trying to embrace both Albers' experimental approach of employing a material as a driving force in an open-ended creative process, and Otto's scientific rigor in conducting design research. But I think we also try to sort of locate that in a contemporary context of design computation and new ways of fabrication. And we hope that as this is pursued not only as a technical but also as an intellectual venture, it contributes to the emergence of a novel material culture in architecture. And I think that's the important aspect, that it's above and beyond being a kind of technological contribution. It is a cultural one, which is probably emblematic for the abilities that we already have now. So what I will do is I will look at a couple of these aspects of how we can actually make material a driving force in design by focusing on some of these aspects like materiality, materialization, material structure, and material performance. And I think it's also important to mention that we usually pursue this investigation by using the format of the pavilion as a vehicle for experimentation, for seeing how these kind of emergent technologies really carry new spatial and structural potentials. Because the pavilion as an architectural type is sort of suitable for these kind of investigations. So let me start with the chapter on materiality, and which really looks at how design computation enables the integration of material behavior in the kind of genesis of architectural form, structure, and space. So I will introduce that by looking at this project, which was a kind of collaborative undertaking between my institute and the Institute of Jan Knippers, which is a structural engineering department. So what is important to understand is that when we actually embark on a research that investigates the possible integration of computation and materialization, we begin our investigation on the microscopic scale of the material, which in this case was wood. And on that sort of microscopic level, it is actually really revealed that the various layers of the wood cells and the cellulosic microfibrils, as well as the lignin that make up the kind of wood tissue that is the material, actually really work like a natural composite material. And because of that, wood has a lot of very similar characteristics as synthetic composite materials that you all know, like glass fiber or carbon fiber. That's also why a lot of wood products have been replaced by glass fiber products like skis, the vaults for pole vaulting, all these kind of things. And what is particularly interesting for architecture is that these materials all have a high level of strength combined with a low level of stiffness, which means that you can elastically bend them and they still have a structural capacity. So if you look at this, this is probably the most primitive form of material computation. You have a piece of wood, you give it one very simple input, which is pull on the support point on one end, and then the material computes the parabola that is relatively complex. But it has already been known since the 17th century. That's what Bernoulli actually called the elastica curve. Despite this sort of elegance of the movement and the simplicity in doing that, this is never used in architecture. And that's because we as architects are not able of drawing material behavior, and usually we can only build what we can draw, which means that this is something that we cannot work with. So it is no surprise that there are only a very few examples of elastically bent architectures, such as the vernacular architecture of the Mandan people that you can see here in the southern Iraq, which actually work with elastically bent reed bundles, or the timber grid shells that were developed by Fray Otto, which are actually exciting because they start off as a totally regular planar grid that you can see up on the left, and then they're only sort of jacked up at a couple of strategic points, and then they totally by themselves find the structurally stable double curved form entirely more or less by themselves based on the elastic behavior of the wooden elements. So it's sort of physical computing as a construction technology that also results in an extremely materially efficient system. So based on a conversation that we had with Fray Otto, we were interested in further developing this sort of idea of elastically bent architectures in the context of today's technologies. And for that, we started with a kind of series of tests that correlate the physical and the computational behavior. And from that, we derived actually quite a simple system, which consists just of two strips that you can see here. This is actually a material simulation. And then if you actually connect these strips in differential distances, you get a system that looks like this, where the tension region in one strip keeps the elastically bent region in the other strip in place. And by that, you store energy in the system, and that actually makes the system stable. This is what we call a behavioral model. We have developed techniques of turning that into a constructional model through computational techniques that basically anticipate the possibilities of the machines that you're going to use. I will talk about that a little bit later, but the critical point here is that it also doesn't take sort of the knowledge of an advanced structural engineer to understand that there are serious weak points in that system. I mean, where the two strips actually meet, the structural depth is 0, and that means it's very, very weak at that point, which would probably make every sensible sort of engineer withdraw from working with this system. Luckily, my colleague Jan Knippers is an incredibly innovative engineer, and the two teams working together figured actually out that by introducing irregularity in the system, you can actually distribute these local weak spots so that they don't compromise the stability of the overall system, basically by letting the joint points oscillate along the structure. And this sort of distribution of the joint points and its morphological and architectural consequences became one of the main drivers in the computation design process, so that here, strategically introducing local irregularity really allows to achieve global stability, something that is very counterintuitive. If in this case, all the joint points would be at the same position, the structure would actually collapse. And it gains stiffness by being irregular. This was also verified by a fully fledged material simulation that you can see here. And I think this is a very interesting sort of computational approach which really shows you how the pavilion finds its final shape as the equilibrium state of all interacting elastic elements. So this is obviously far beyond all the notational tools that we usually have available as architects. And because here, the pavilion really finds its final form by computing on the kind of material level. What is interesting about that is that construction becomes incredibly simple. You basically start off with these regular elements, you do the CNC milling, and then you show up on site, and you basically just have to put these pieces together at the defined joint points, and they find entirely by themselves the correct shape and position. So again, in other words, even in full scale on site, the material itself computes the shape of the pavilion. And what is interesting here is that this final shape does not only unfold quite a unique architectural space, it is at the same time very efficient with the employed material resources. So here, the entire structure, which had a diameter of more than 12 meters, could actually be built from extremely thin sort of wood lamellas that are only 6.5 millimeters strong. So this super thin skin is at the same time the load-bearing envelope, which actually needs to meet all the stringent regulations of a German building application. For all the projects that I show you, we go through the full process of getting a building application with all the kind of related requirements of the load-bearing verification, all that. And it is at the same time the light modulating and weather protecting envelope, which in this case actually touched the ground topography on one side and actually opened up to a kind of large free-spanning opening towards the adjacent public square. So what is interesting is that inside, the kind of emergent toroidal space has an incredible level of spatial depth because it can never be perceived in its entirety. And that is even further enhanced by the direct and indirect illumination that results from the kind of structural bending of the envelope. So in addition to the kind of exploration of these kind of architectural qualities, the construction of these research projects also allows us to do a bit more a kind of scientific investigation or verification, which in this case was done by comparing the results of the computation design process, which you see on top, with a kind of comprehensive laser scan of the geometry that the material computed in full scale on site, which is here shown at the bottom. So this is a scan of the full scale structure. And because that really only showed very minor deviations, one can see that this sort of integration of material behavior and design computation is not a kind of idealized or far-fetched goal, it's actually really a feasible proposition. And more importantly, one can probably also see that the project nicely demonstrates how focusing the computation design process on material behavior rather than geometric shape allows for unfolding performative capacity and material resourcefulness, while at the same time expanding the design space towards formerly unexplored architectural possibilities. So I think in that project one can really say that the material no longer remains to be a passive receptor of a kind of pre-designed shape, but becomes an active generator of design. A second aspect of investigation that we do focuses on how we can actually make the actual materialization processes an active generator in the design, in design, not assuming that fabrication is just something that a machine does to fulfill your design or to realize it, but actually how the possibilities of the new fabrication technologies that we have at our hands can become also kind of stimulus for new design approaches. So I show that along this project, which actually started with a very kind of straightforward aim, namely looking into how we can use industrial robotics And this is an industrial robot. It's kind of this orange machine that has been around for more than 40 years in the automotive industry, slowly makes its way into building construction. This is a machine that's interesting because it's actually very cheap compared to what it can do. And that allows us to obviously think very differently about, for example, traditional wood jointing techniques, such as the finger joint that you can see here, which when we actually machine it with this kind of robot, we can extend to very complex blade structures that can have different blade thicknesses and so on. And we have developed ways of actually systematically and mathematically describing the sort of the space of possibilities that these processes give us through simulation. So we know exactly what kind of blades we can manufacture, and that obviously then begs the question, how as designers do we explore this space of possibilities? And I think this is when actually the relation to biology becomes very interesting. Because arguably, and this is what Julian Vincent nicely says in his quote, in biology, material is actually expensive, which means it's sort of metabolically expensive for the organism to produce. But shape is cheap. And as of today, the opposite was true in the case of technology. And arguably, that has actually conditioned our architectural design thinking. So once you actually use this kind of robotic fabrication and you know what you can do with it, shape becomes actually cheap. And that means that we can probably save a lot of material resources by having, in the end, more shape. So in order to productively use that, one has to really understand the behavior of these systems. And again, I think it's very straightforward, and you don't need to be a structural engineer to do so, by knowing that these finger joints are very good in withstanding forces in the plane of the sort of shear forces along the plane of the plates. So if the plates want to do this, they're locked in place. Very bad in transferring bending moments because they're like pivot joints and cannot withstand any tension forces. So again, engineers would consider that as a big challenge when it comes to designing a construction scale plate structure. However, it's interesting to note that in biology there are systems that have addressed exactly that challenge. And one that we found with our collaborating biologists from the University of Tübingen is the sand dollar, which actually is a shell that is made from discrete polygonal plates that you can see here, and these polygonal plates are actually connected by the biological equivalent of our sort of craftsman-derived finger joints. So that means that obviously this organism has found a way to transfer all the forces that are acting on it into these kind of shear forces along the edges, because if not, it would collapse. So with the help of the biologists, we extracted the rules that govern this behavior, this kind of performance capacity in the biological realm, and transferred them into a computation design tool that then enables the designer to explore the kind of space of possibilities of the physically producible through the filter of these biomimetic design rules, which in concert with spatial and contextual criteria lead to a kind of very specific blade morphology. And again, the distinctiveness of this architectural form is actually mainly governed by the fact that each element responds to its specific requirements, which then again also means that each element is inherently different, which in this case means that you have more than 800 different plates with more than 100,000 different finger joints, which is no longer a problem if the fabrication logic is part of the design process from the very start, so that you can actually drive your robot from your design environment. So this is the way that these plates are made. Here already the plate is pre-trimmed by the robot on the turntable. So this is one robotic unit. The turntable is coordinated with the robot. And then the robot actually starts to cut these finger joints. And you can imagine that the tolerance of the joint is basically the tolerance of the tool, which is in the sub of a tenth of a millimeter range. One plate takes 3 or 4 minutes to build. And again, the interesting thing here is that there's a lot of intellectual investment 5 to 6 researchers working on that for a year together with 15 master students. But in the end, the system is very straightforward and very cheap. So you basically have this puzzle of plates. Then the nice thing about a puzzle is that it's self-correcting. So once you actually put the pieces together, you know that they have the right shape. And because of that, you can actually build a shell in a very unconventional manner, namely from the bottom up, because you kind of know that the keystone will fit. Again, more importantly probably, is that this sort of quite unique modular wood shell demonstrates a high level of structural possibility, but also quite a unique architectural potential. And all that with a system that is really only made from plates that are connected with these finger joints. So there's no other connection. So here, again, the amazing thing is that the structural capacity was demonstrated by using only 6.5 millimeter plates. So this entire system, everything you can see on that slide was actually built by using less than 2 cubic meters of wood. So I think it's a nice example how sort of an expressive architecture does not necessarily mean an excessive use of material resources. On the contrary, I think here sort of architectural performance or architectural performativity and structural performance occur in a kind of on a new level of convergence. What is interesting also to note is that on the base of these academic projects, we were able to get research funding for doing an actual permanent building, which is this exhibition hall that was erected for the Landesgartenschau. So here we had the chance to bridge the gap between academic research and the construction industry by actually inducing innovations on 3 levels. The first level is that we bring our robotic equipment to the timber manufacturer. So this is now produced in a professional realm. And the interesting thing is that the robot is actually very, very small and a very compact, low-cost unit compared to all the other machines that a timber manufacturer has. The second aspect is that we were able to reduce the construction system to a single plate structure. And the third innovation is that we were able to use wood that is usually deemed unsuitable for construction, especially in Germany. And this is actually beech wood, which is a hardwood, which, as you can see from that slide, is actually not used in construction at all. Actually, almost 50% of the beech wood in Germany is just used as firewood or thrown away. And that's interesting if you look at climate change and you realize that the entire Central European forest will actually change from softwood forests to actually beechwood forests because the climate change leads to the fact that softwoods, spruce, pine will no longer survive in Central Europe, and it will all become basically hardwood forests like beech. And this is even more remarkable if you figure out that these hardwoods actually have much better mechanical properties than the softwood. So in a sense, we're working with inferior material that will no longer be there in a couple of years. So I think it's interesting that here we found a new way of utilizing this kind of material resources. So the way that this system is actually done is it's kind of pre-formatted on this digitally driven plate cutter. And then these kind of pre-cut plates are machined by the robot and are ultimately also drilled by the robot to form this structure that is a single plate system. So this is actually the load-bearing structure system. That's all there is, sort of 50 millimeter thick shell. And here, that's also the important aspect, is that these fingers remain to be the important structural feature. They take actually 10 times more forces than most other forces that are occurring. There's another aspect that is also challenging, is that obviously that means you have to work with planar elements. Now, if you want to use planar elements on a double curved surface, it becomes a bit involving. So what we did to overcome this challenge is that we actually defined every blade as a kind of agent. And then we didn't even attempt to draw or model the plates, but we assigned a certain level of intelligence to the computational plate, which knows about the geometric constraints. The agent knows about the constraints of the robotic manufacturing, and especially it knows about the constraints of the building code and the building standards that need to be fulfilled, especially on the kind of screw connection level, which are crucial to get it through proof engineering. And with all that knowledge, the blades begin to venture around and find their own sort of configuration by themselves. So it's really that the blades themselves explore the space of the fabricable and sort of find a suitable, structural, and producible condition. And this is actually sort of showing that this works with this kind of distinctive transition of of blade geometry. And it's also important to understand that this has significant architectural consequences because the timber is what you see on the inside. That's the architectural surface. It's also interesting to note that this building was completely digitally fabricated. So it is a kind of fully equipped building, has insulation, cladding, everything, and all that is digitally fabricated. So we have a 5-axis insulation layer, a membrane, and then the system is actually set up on site in a very short amount of time. It took 3 weeks to prefab the whole building, and it took 8 days to set it up on site. Because again, it is a large puzzle that can be simply erected, and then the kind of additional layers of insulation and waterproofing are added. And finally, an external timber cladding is applied so that on the outside you have this timber appearance, but on the inside you actually see the actual structural plate shell. So I think it's interesting to note that the high level of sort of coordination between the kind of plate morphology, the facade elements, which I think is a kind of evidence of the kind of ability of the agent system to derive that. And it's also interesting how this kind of distinctive shape of the blades becomes a key architectural feature for a space that has a central contraction and then opens up towards this space that opens the view towards the landscape. And again, I think it's interesting to note that here the kind of spatial expression does not come at the cost of resource efficiency. In fact, the entire shell could be built with using just 12 cubic meters of wood, which was actually utilized entirely because all the offcuts from the plate machining were used as the hardwood flooring. So 100% of that resource was utilized. I think it's also interesting to see that the 50 millimeter blade is the entire structure system, which actually means it's a very cheap construction technology. And just to give you an idea, if you really look at it in proportion, our shell is actually half as thin as an eggshell in terms of span to depth relation. And then another aspect that becomes increasingly important is that the entire, everything, all the materials that we used were sort of grown, sourced, processed, and fabricated within 200 kilometer radius. And that is obviously of significant ecological advantages if you look at the kind of usual transport routes that building materials take. So it's, in a sense, it's a kind of new vernacular structure that takes advantage of the only material resource that we have in southern Germany, which is actually hardwood that is locally grown. So there are a couple of more pictures, and I think what is also interesting is that we did a couple of additional feasibility studies after that, and the system is actually so performative that you could easily have it span 120 meters in length, 30 meters in width, and it would still be less than 10 centimeters strong. And I have a little video that sort of summarizes that process. All the trees are actually sourced locally, and they have time to apply with the couple of minutes, I could show you also sort of a very different approach. Because in a sense, I think these projects are still sort of conventional in many ways because they build up a larger system from a large number of small elements. But if you really begin to engage with natural construction, we see that in biology, very often something very different is the case, where an entire structure is built from continuous elements that are differentiated regionally. So this was an investigation that we conducted along this research project, which is, again, I think, and this is always important to say, these are multidisciplinary undertakings where architects work with engineers, with biologists, and with process engineers on an eye level and hand in hand. And this is what enables these kind of projects to happen. And I think this is aligned with the kind of computation design culture. So here the aim was really to do the opposite of what I showed before, to build a kind of lightweight shell from actually just one continuous materiality that is locally differentiated through robotic fabrication. And an interesting biological example of that is, for example, the lobster shell, which here you see in the cooked state, which means that if you ever had a lobster for dinner, you know that there are certain parts of the lobster that are super stiff and very strong, like the crusher and the pincher claw, and there are other parts of the lobster that are very soft and elastic, which you can see in the sort of engineering diagram of your lobster meal experience. But it's also interesting to note that these very different material properties are actually achieved by one and the same material. So the whole lobster shell, actually including the eyes, is made from one material only, which is a chitin fibers that are embedded in a protein matrix, which means it's a kind of natural composite material that allows for all this kind of differentiation on the material level. So what we did is we investigated different parts of the lobster with the students and the biologists under the microscope again, and extracted sort of the principles behind this kind of performative fibrous differentiation. And then we also began to investigate advanced ways of composite manufacturing, because these natural composites are ultimately very similar to technological composites such as carbon fiber or glass fiber constructions. And some of you may know these systems. Sort of in the last 10 years, we have gained the possibility to actually lay fibers individually. But these projects or these kind of processes always require a comprehensive mold. So this is the mold, for example, for a wind turbine blade, which is definitely building size, sort of construction scale dimensions. So in a sense, we think about composites in the same way that we think about concrete, which is that it's an amorphic material, which always means that what you get as a form is actually just the imprint of the mold, which requires you to build these incredibly elaborate and expensive molds. So we were interested in actually teasing out the actual morphic characteristics of fibers, and by that not requiring any molds, by reducing actually the formwork to a kind of linear scaffold on which the robot actually lays the fibers, and by that sort of generates an embedded mold onto which subsequent layers of fibers can actually be applied. So once you understand this very different logic of arranging material in space through the digital machine, you also begin to understand that this gives you a whole range of material possibilities. So it's not that you look up material properties in a textbook and say, aha, that and that concrete has this and these properties. You can actually design the material to perform in the way you want through the fabrication process. We actually devised this kind of prototype in which we follow the biomimetic rules that in areas where you have a lot of forces accumulating, you have strongly directional fibers, where in other areas where the surfaces are more sort of the spatial sort of boundary between the inside and the outside, the fibers take on what in biology is called a helicoidal fibrous arrangement. And these principles were then embedded in kind of comprehensive method for developing design techniques that unfold actually quite a rich repertoire of architectural morphologies based on the quite complex relation between the geometry and the manufacturing process, where you have to understand that only at the very end of the fabrication process the part takes the final shape, because if you wrap fibers around a fibrous scaffold, it changes through the entire process. So our engineering partners simulated this process so that you can understand what the kind of pre-stress is with which you need to lay the fibers to get a kind of given result. So this is the fabrication setup that we developed for this project, which is basically, again, a kind of 7-axis robot where you have this temporary scaffold onto which the fibers are then laid. And this is obviously a process that is radically different from all other construction processes that we know. Here, instead of an assembly of parts, the entire structure is actually wound from one continuous fiber. And in this process, the shell is actually built up of successive layers of glass fibers, which are the white fibers that are transparent, and the actually structural carbon fibers, which are the black fibers that you can see here. So the glass fiber becomes the embedded mold onto which the fibers are applied in a kind of resin saturated state. So you see the resin bars, fibers run through the resin, and then once they are applied, they slowly harden, so that you can, in the end, you can take the scaffold out and you end up with a very thin shell composite structure, which in this case consists out of more than 90 kilometers of robotically laid carbon and glass fiber, but the shell is only 4 millimeters thick at the thickest point, which actually allows for quite an amazing level of transparency, especially when perceived from the inside. So I think it's interesting that synthesizing these kind of new possibilities of the machine with the kind of ability of the material structure itself really allows one to come up with a novel tectonic system where you can still understand the construction logics by the kind of articulation of the structural carbon fibers. And all that forms one continuously constructed materiality, so no nuts, no bolts, just fibers, which also unfolds quite a kind of unique haptic sort of quality. And I think it begins to suggest a very different sort of possibility for tectonic articulation when the designer no longer just designs form, space, and structure, but when he actually begins to expand the design process towards designing the fabrication and production processes from which form, space, and structure unfold. I could leave it here. Maybe I should do that now because of time constraints. I just was made aware that it should not take too long because we have another lecture after that. I can just say that we also managed to do this on a kind of sort of modular level so that you can actually transport these elements. And if you're interested in seeing more of that stuff, you're more than welcome to visit our website where all these kind of projects are portrayed and we can get the information that I now had to skip. Thank you, anyways.
Okay. Thank you very much to Professor Menges. Quite a very interesting and inspiring lecture. And thank you very much to Professor Roberto Bottazzi from the Royal College. Here, again, we are in the field, for us from Milan, a quite innovative field of action of our research. It's it's quite interesting, inspiring also that that research of Professor Bottazzi that is graduated in Florence, but now he's teaching in Royal College of Art in London. Roberto Bottazzi trying to study the impact of the new technology and the globalization on architecture and urban design. And as we saw in the previous lecture, it's quite important to combine both a theoretical point of view and a very design-based approach and very practical approach. And in Italian we are speaking about a pratica teorica, and I think that it's quite important also in that for us new field of action try to combine the two point of view. The research of Professor Bottazzi is not related to an object, but is related to mapping. That is also another very important and relevant part of our research as architect and urban designer and try to, through that kind of new way of mapping the environment, trying to envision different ways to organize, we could say, to interpret, to analyze, to interpret, and to project the urban environment. Also in our project, we're trying to deal with the problem of the map. We have some fights sometimes because, and the same thing when we are speaking about new shape, new form, we have to change our point of view, and it's not so easy. So I'll leave the floor from Professor Bottazzi, and I hope that after we could discuss together also with Professor Menges. Thank you very much.
All right. Thank you very much, Antonella, not only for the introduction, but mostly actually for the invitation. It's not easy to follow from Achim's work, but I'll do my best anyway. So yes, the presentation is a quick overview of the work that I do. Every now and then I will jump inside academia and outside academia. Sometimes I will make full credit of it. Sometimes perhaps you will only find it on the screen. My kind of work starts from, let's say, using computer and computational for computational design, and it starts in a slightly, I should say, more conventional way, as in looking at the actual architectural space. Here is a winning entry for a competition in Arnhem, developed with a London-based office called Cora, in which we worked on a number of objects that were scattered along the landscape, taking vaguely the shape of a parachute and animating the public landscape of this new development in the edge of Arnhem. The work here is, I primarily show it because the work always tends to look at the computer from both ends, no? From what you can see on the screen of the computer, but also from what you can see from where you are standing at the moment, that is the back of the computer, the range of cables, connections, networks that wire this machine into the physical space that surrounds us. This obviously is the stuff that you can do when you sit on my side of the computer, mostly anyway. The project was fully developed. It was a glass-reinforced cement, the material, and in the end, these large shells, which were ranging from about, let's say, 4 meter tall and very thin, about half a meter wide, all to the opposite, basically, ratio of dimensions, were all built out of 25 mil shells, basically, which were actually, of course, supported by a steel frame which was sitting underneath. Grossmax was the landscape engineer that worked with us on the rest of the landscape. Other projects of that kind of engagement had to do with smaller pieces. In this case, is a table for an exhibition design, which was manufactured by a quite interesting company, which is based in the UK, called the Codec, in which the entire piece was milled, CNC milled out of polystyrene. This is about 2008. But you know, at some point my research also, I decided to take a slightly different direction, which is mostly what I'll be talking about today, and to try to problematize statistic information such as this one, no? That the large amount of data that are produced in the world are having an effect on not only the way we live, you know, pretty much all of you have a mobile phone and so on and so forth, you know all that, but also in the way in which the city is organized. Of course, you probably have heard of the large debate about the smart city, and you could say that the work tends to situate itself in that area of interest. When you start analyzing large amount of data, of course the computer is pretty much the only tool that you have available in order to interrogate the data in a way that it's first of all possible, but also through methodologies which are not available to just human faculties. And that is where the work is at the moment, and that's actually the work that we are developing at, you know, with, of course, at a small scale throughout the workshop. That is how to look at the city through data and how to use the computer as an interface between the physical space of the city, the virtual space of data, and, of course, us, you know, the designer of those conditions. I also like the idea that most of the computational or data that we have today no longer are associated with computers. They are also distributed in reality or in materials, as in the previous lecture was made very clear. And one of the interesting, I think, critical points is to try to also challenge images like this one. This is a map of the internet, which is, of course, an incredibly fascinating image, but somehow beside, let's say, the aesthetic allure that this image has, it's very difficult to interrogate for its meaning. You know, this image really doesn't reveal much sense of agency, interaction, or ownership, which we know now are important elements when it comes to the virtual space of the internet. Because the physical space of the internet is also looking much more like this. This is actually a photograph taken by Eflux, they're quite good, quite famous and good art magazine, of in Tahrir Square during the revolution in Egypt. Or at the opposite end of the spectrum, in terms of scale, it also looks like this. That is the range of fiber optic cables that take our data throughout the world and actually form the internet. So obviously there is a kind of combination of technological, political, social, and cultural elements that begin to form a strange condition, right? That we could identify our present society with, at least in the West, mostly. Most of this work became somehow clearer and more apparent to me by looking at a more specific physical event. This is a piece of research that I started a long time ago, and I'm very happy to see it ended yesterday, and I'll explain in a moment what that means. On the G8. I looked at 10 G8 meetings between 1999 and 2010, so you could say 11. And as a way to understand how digital physical space form or help us to understand our present condition. It's very interesting. This is not a G8. I should declare this first before someone else picks that out. But from 1999 till 2010, the G8 were pretty much the center of global politics, you know, where the key event, one of the key events throughout the year where the world was coming together to discuss global agendas. And from 1999 all the way to 21 and all the way to 2010, the G8 became an incredible, I think, stage to understand how different issues were playing out in the public space. This is actually where the actual meetings were held when the Sea Island, the American G8 took place. Most interestingly, there was a very sharp contrast between the physical transformation of the space and the proliferation from 2000, 2001 onward of the digital layer that was going to be overlaid in the cities. I thought that that was causing quite interesting questions in terms of how to represent and therefore understand and eventually intervene in these places, and that was forcing a different way to represent it. So part of the project was to abandon normal plans or sections on elevation or traditional diagrams and try to understand this space only through scalar relationships. And when you understand it like that, of course, you have a quite different image of the public space, a quite, if you like, almost rough adjacencies of very advanced technologies and very low-tech, almost brutal, if you like, interventions in the public space. There's a complex network of physical and digital actors and agents that come together to form this temporary city which only exists for 3 days and eventually vanishes, which I was trying to map again through relationships of scale and agency. There's also physical reality to these places which get temporarily reconfigured, and there's even a highly immaterial element of these spaces, which is here represented by the color tagging that is attributed to any participant to a G8, or at least in the time period I looked at. So this is, of course, the most immaterial element, which is law. Beside the G8, one of the other reasons why this research on a kind of smart city, you could say, was interesting me was that more and more other situations, this is London in preparation to the Olympic Games, we were looking at this complex mix of different technologies and different attitude towards public space that were being unfolded. This is actually very close to where I live. Yeah, like I said, I'm happy because last night this book was launched, and the book contains a quite extensive paper, if you like, on this long-term research on the nature of the G8 public spaces. A second project I want to talk about is a slightly different one, and it's a project that was commissioned by the city of Xiamen in China. It was done in collaboration with Cora, the same office that I mentioned before. And the idea is basically to create a master plan for the city. One of the concepts that we wanted to develop was, first of all, to design a master plan around the issue of energy as a driver. And of course, the second thing that we had to deal with was the kind of rapid demographic growth that the city of Xiamen was planning. And the third and final element was that there was no official, comprehensive, citywide planning document for the city. We made a proposal, and which was basically that the city could have skipped to have a traditional master plan for the city and adopt digital technologies as a way to create its own master plan. We proposed to make a kind of demonstration piece first, which is what you're looking at here. The centerpiece is a 4 meter by 4 meter model, which represent the entire metropolitan area, and is informed by cybernetic principles of feedback, which were mostly influenced by the work of Stafford Beer, the British cybernetician that also worked on planning, in which the citizens were able to interact with the model, see energy patterns of distribution and consumption, and somehow engage with an energy-based master plan. The actual piece is eventually divided into tiles, which are about 300 millimeters square. And underneath this tile, a grid of LED lights, which are interactively controlled, determines the degree of luminosity of the light itself. There was a kind of computational model which we internally developed in order to gauge a number of parameters that had to be working together. And eventually we decided to manufacture the tiles by rapid prototyping them, and therefore having a very thin, about actually a millimeter thick edge to the model, which provide us with, I suppose, a number of advantages. Not only practical advantages, of course, because we had lights underneath, but also created a complete uniformity between man-made and natural. So the city was actually made of one element, no distinction. And the second thing was actually that it created a quite delicate landscape, almost like a veil, if you like, was floating above the city. Perhaps that sort of more, if you like, emotional or experiential way of associating with the model was also useful to suggest that the city is still a delicate organism that needs a certain amount of curation. Underneath this thin and quite poetic level, there was actually a jungle of cables and lights and circuits eventually wired into Arduino circuit boards, eventually wired inside computers, which was controlling this complex system of lights. The final result is, of course, one in which the model changes quite radically. Its look when the lights are activated, and the pattern of consumptions can be of energy consumptions are visualized. There are a number of variables which have to do with the kind of energy or the kind of source of energy that affect the color of the light. There are other things that we could manage with the computational model having to do with the kind of effect of that light, meaning the closer the LED light to the skin, the more kind of point light you get, and of course the opposite if you lower the actual LED light. And the model was eventually wired inside the computer, and therefore both real data and other data that we were actually adding to the model to also show how things could have been adapted were visualized. The citizen interaction in this case wasn't so much to design the city, but literally to understand their own environment through pure flows of energies. Another project I worked on subsequently, this master plan for Xiamen, was actually a project that was developed for an art competition in the United States. And one of the things that was really interesting in the work in Xiamen, which we couldn't quite achieve, at least through the kind of short time frame we had at our disposal, was that eventually the possibility, not unlikely the work that in the 50s and 60s people like Buckminster Fuller or Stafford Beer were doing, eventually computation could have been a tool to wire the behavior of a city inside very large global forces that are otherwise very difficult to visualize. Now, there's always one example that I use, which is that open air mine in Australia have a computational model that is directly wired into the price of gold and the fluctuation of price of gold, and that fluctuation affects the speed at which the actual mine proceeds in excavating into the ground. And this incredible disjunction of scales and also of material and immaterial flows is often something that has to do, of course, with living in a global world, but also very hard to grasp otherwise. So in this project, the idea of sight unseen, what should we visualize of a site, that we can't see otherwise, was working along those lines. And there was, I suppose, a kind of coincidence that this place was in Tennessee, exactly on the 35th parallel of the Earth. And that was the datum, that was the starting point of the project. And 21 major cities that also shared the same geographical position were mapped along this ring, which eventually was also animated by data about these places. The data are distributed in a kind of material-in-material, along a material-in-material gradient. No? So the inner circle have to do with things that are highly tangible, like access to fresh water or level of natality, all the way to the opposite end where the more immaterial elements such as internet connection and so on and so forth are mapped. What we are looking at is, of course, a computer model, but is the simulation of the final piece, which was a piece to be experienced through augmented reality. So the final element is a 35 meter wide ring with all these different data which are tagged and therefore are accessible through your mobile phone. The source for the work is the quite famous CIA fact book, which is an excellent, actual, up-to-date atlas of the world. And there's a series of kind of relatively simple computational tools that are used to orchestrate the fluctuation of the data on the database with the actual augmented reality piece. So in the end, the piece has, again, not unlike previous examples, has the ambition of working both as an analytical tool, but also as a more kind of experiential, almost like an installation in a public space. This is a brief text of how the piece worked. The piece, I must say, this is also a couple of years ago, had to be, the polygonal count has to be kept within a certain limit in order for average mobile phones of the time to be able to compute the model with enough kind of reaction, quick time reaction. I also generated other visualizations of the project which try to forget about this limit, polygonal count limit, and almost create this sort of shower of data that could also be seen as varying over time and so on and so forth. Again, these are all elements that are accessible through the database. So the database is both as Lev Manovich says, the database both as an analytical tool but also as a symbolic form for our present culture. A few more projects, quite small, but I still think quite interesting. This one was developed with Italian architect Guido Incerti, and it is a study commissioned by Nestlé for the future of retail. This was also commissioned in 2011, in which again we started looking at the presence of what we ended up calling art systems and light systems inside the retail and the retail area, and proposed 3 future scenarios for the brand, or at least 3 ways in which the brand could have engaged these emerging technologies at the time, which are here listed as a store beyond the store network condition and experiencing / immersing in data. The schematic sort of approach, this was just a kind of initial study, was one in which, of course, the use of screens could have expanded the role of the retail space outside the physical limits of the retail space, but still operating within the city. And as said before, could have used the intelligence of databases, as often experienced when we browsed for something on Amazon, to create a network of related products. Of course, Nestlé, as you know, because the expo is about to open, Nestlé operates in the field of food production, And it's quite interesting to relate the world of data to the kind of hard reality of food, how it's manufactured, how it's produced, how it's shipped, what kind of elements are interfering or helping the supply chain that moves basically a raw product from somewhere to a shelf in your supermarket. Or finally, the use again of augmented reality to enhance the retail experience in the actual shops. This year, I have been working with this company called Big Art Mob, also based in London. These are research projects that mostly take place through the Royal College of Art, where I teach, where I've been teaching for the past 9 years. And Big Art Mob is a company that was launched a while ago by an initiative led by Channel 4 to map public art in London initially. It runs a normal, basically, database of public art, which has now expanded well beyond London and runs on a quite traditional platform that is on Google Earth as an additional layer. The research question we developed together was to explore what kind of limit in terms of scale was possible for the company to map. And of course, being an architect, the focus was very much in trying to integrate buildings inside the database itself. Of course, the relationship between how buildings are archived runs along the actual, three-dimensional, if you like, constructions. Has a lot to do with software and the CAD packages we have at hand to model buildings. We wanted to challenge that. We devised a case study, which was basically where we ran all our tests on this experiment, in which we started using a slightly different platforms, like this one, which Autodesk developed, called 123D Catch, in which with a relatively simple set of photographs of an object, a three-dimensional mesh is reconstructed for you. We had some issues with that we had to overcome. One was that of course, Autodesk as a proprietary software, 123D Catch is a proprietary software, and therefore somehow we wanted to have a more open, at least in terms of accessibility, approach to the problem. And also, you don't really have any control in the way in which the process takes place. You upload the photographs and you get something back, and that's it. So we started to test a number of different options, and eventually, and also the possibilities for actually manufacturing buildings or scans of buildings directly through rapid prototyping. And eventually we found a different kind of software, which I will describe in a second, which is an open source software called Visual SFM, which some of the students are also playing with these days, which allowed us not only to control the process itself, but actually to open it up much more. And that is a quite interesting element that emerges when you work in this area, that somehow the construction of the tools to achieve a certain result can be as important as the result that you want to get. So trying to understand the kind of initial position and try to lower the entry point, both in terms of technical difficulties, but also in terms of sort of social engagement, if you like, was interesting. The software, like I said, is quite simple and allows you to generate three-dimensional point clouds of your building, which you can eventually, of course, translate into meshes and give it a more a look that is, let's say, closer to the actual architecture that you are trying to map. There's quite a lot of interesting work in terms of the granularity of the scans themselves, or perhaps this is the part that I like the most, in the stuff that happens behind the actual interface of the software in terms of correlation of elements, and the actual output that is generated, which is again a database. In this case, in forms of an Excel sheet, in which a number of parameters are listed. Through that, we started a number of experiments on the visualization of this information, how it could have been made accessible to a large public. And also, we started also to test it on other elements, in this case with students as well, starting to really understand how data or architecture can be seen by an artificial eye, and starting to generate visualizations in which the actual database, the actual the numbers are interrogated in a slightly different way. So playing colors versus geometry, or trying to find shape detection, or elements within the facade, and foregrounding it in order to really represent architecture in a different way, in a way which is otherwise relatively complex to the human eye. From these sort of point clouds and spatialized reconstruction, we also went into more analytical stats in which the color distribution are analyzed, and this is very much work that I'm still pushing for, and even if this sort of short research project with this company has now been brought has been finished. We've concluded it. The very final project I want to talk about is also about this kind of large data sets and their role in the city. It's a project that I never really talked about, but because one is recent and B is also a project that we are, I suppose, still working on in a certain way. It was done with Antonella and with a musician and software designer Martino Traversa and Raffaele Pe, which I'm very happy to see also in the audience today, in which it was a proposal for the city of Bristol, which was titled Bristol Madrigals, and it was an idea to create 5 kind of stations throughout the city in which sound could have been used to enhance, augment the experience of the city. The technology behind it is a technology called ambisonic, which has been developed about 30 years ago, I understand, and allows you to position a sound in space. Of course, a more commercial version of this technology is found in pretty much any headphone set that you can buy. And we found really interesting the idea of treating sound as a proper material, in a way with the same characteristic, if not more characteristics, of the kind of materials that architects are accustomed to. So our role in the project was actually to begin to understand how to visualize this three-dimensional set of sounds, which has a dynamic component, and also as a material itself. So we developed first initial some kind of interfaces, and this is not our work. We also looked at the actual technology behind the position of the speakers in space, the digital interface that links the physical space of the recording studio, in that case, with the software space in which the project can be simulated and orchestrated. And eventually, these are sort of initial studies, we started developing a series of point clouds, again, in which the information from the music played through these systems and its exact position in space could have been linked to a digital model that could visualize the architecture of sound, basically. And eventually, we proposed to use, again, augmented reality as the interface between actually the user and the space of the city. So it's a quick overview, but you know, I suppose it gives you a rough flavor of the things I do when I'm not here. Thank you very much.
Thank you very much to Achim Menges and Roberto Bottazzi for their very interesting lectures. Ingrid, Vini. Ingrid, come please. Two very interesting lectures that talk both of the digital question, the interaction between the digital culture, the digital tools and architecture, and the society and information and relationship between us and space, virtual space and real space. The topic, the projects, the themes are very interesting. We have here many students, doctoral students, tutors, professors. So I hope that you can have some, you can put some questions, remarks to express your opinions and to have some discussion with our lecturers. Vieni, please come here. So, please, because the hall is not small.
Sì, thank you to both the contribution, which I found very engaging for a school where I studied 5 years ago, and I had the feeling that this was the very first time where really 5 years ago I wanted to see something like that in this school, and it didn't happen. And now I feel that something is changing in the direction of a more global discussion, which I find very positive and very actual in current universities. But apart from that, talking about the digital question as it was posed, I was surprised to see how the discussant had this implicit need of going towards an encounter between the virtual reality and the actual reality. So the way I saw you wanted to use softwares and the computer was in reality was trying to push the virtual reality towards the construction of something very physical and material. In the work of Achim was very clear that the construction, the virtual construction became then a physical building, while in the case of Roberto, I had the feeling that what was mostly material around the city then suddenly tried to become we could say a physical, again the physical image of architecture within the virtual realm. So I was surprised in the sense, I would like you perhaps to discuss on the possibility of use these technologies towards some sort of imagination that leads towards some less material and perhaps or maybe more pragmatic intake towards the contemporary cities and contemporary architecture. And also, and perhaps I would like you to discuss, this is particularly related to the work of Achim. This is perhaps a question that I've seen many times, but I found your work very much related to what we found important in the Treaty of Gottfried Semper and the way we perceive architecture as texture before even defining as a block, as a solid sculpture that we construct, taking away pieces of material pieces from the block, in a way. But this is also, it's profound. I hope to be that this is not too complex, which is a question of style, a question that was very actual in this school 50 years ago, maybe even more than 50 years ago. But I find that these technologies actually brought it back very clearly to our, the way we produce architecture today. And we have two very interesting ways that, despite the way you lead with different agendas, you in fact then become a very significant, I think, way of imagining architecture today. So I let you answer if you like.
Yeah, I mean, there were 3 questions, right, in it. I think 2 are for you, and one I think I can say something as well. And the one that I can say something about is the first one, because I think that most of the research is really trying to understand that the computer isn't a detached object from, let's say, the ecology of all the other objects we have. So that's why it's interesting to look at, the G8, because it becomes very obvious that that distinction can no longer be drawn. Also, so that's one element, and the second thing is that the so-called Web 2.0, which is now, I suppose, an outdated concept even, but I think it allowed us to make that connection much more evident, much more apparent, and therefore easier to work with. So that's that's what the computer means in the work.
But you didn't answer about the texture.
I thought the Gottfried Semper was for you, though. I'll let you go on first.
Okay. Now, because we get into the delicate third part of the question, may I answer the second part, which I think first is important to understand that the opposite of the virtual is not the physical, the opposite of the virtual is the real. That's why the whole idea of virtual reality is a kind of obscure oxymoron in as a first place. But I think it's really, what I try to say is that it is, in my eyes, and in the way I kind of observe how these technologies are developing, a misconception that the virtual domain of the computer is separate from the physical domain of the material, or the real. And I think that's also something that we actually increasingly understand, no? That the computer is actually not just some kind of digital tool that you can use in the same way that we use all the kind of tools, but it becomes more a kind of instrument that allows us to understand the physical world in a totally different way. And I like Sanford Squinter's sort of comparison to the microscope or to the telescope, which allows us to basically engage with things that have always been there, but we were not able to see, and we are not able to interact with, and we are not able to sort of modulate or design. So I think that is an important distinction, because I think the computer is an incredibly interesting interface to the material world. And why I'm saying that is not really my idea is that, and I think that's what we as architects tend to be blind of, is that well, I think we cannot escape that architecture, when it unfolds as our built environment, is physical. No? So when we consider that the cultural and sort of societal benefit of architecture is related to its physicality, then we are also interested in the making of things. And what we need to understand is that the making of things actually radically changes currently. And it's not uninteresting that the idea of cyber-physical systems is something that actually comes from manufacturing industry, where it's assumed that things are no longer made in a way that is kind of just a machine that executes some predetermined steps to produce, manufacture, fabricate, construct something, but all of a sudden the kind of boundary between the physical and the digital is actually broken down, and these things oscillate between those three domains and fluctuate. Well, I think as architects it would be very interesting to start to engage with this world, which not just the optimists in manufacturing assume is the reality in 10 years' time. So I think we will engage a world where making will be something very, very different. And I think as all architects are sort of, or architects that are interested in the physicality of tectonics and space, we're obviously also interested in the way that that may actually have an impact on how we conceive about those physical aspects of architecture, because I think it has, I mean, it doesn't come without a reason that it's called the kind of fourth industrial revolution, where the cyber-physical systems take over production. So I think as we have witnessed with the previous three industrial revolutions, they have really changed every time they happened, our understanding of architecture. So that's in regards to the material physical. That's what I keep long, because that's what is important to me. The question about style, I keep very short, because I think it's totally, it would be very premature to talk about the style of a kind of exploration that has just started. Maybe in the end, if that is a historic category, which I understand it is, I leave it to the historians to do that retrospectively. But I think as a category for generating design, it's I think irrelevant at that point. Which does not mean that formal articulation is irrelevant, but style as a kind of historical assessment, I think is, I wouldn't want to dare to talk about. If you want.
I'm all right, yeah. Thank you.
First of all, thanks for your lectures, and sorry for my English. I have a question for Achim. If I'm not wrong, your research pavilion are temporary pavilions. And I want to know, how do you define them? If only model, prototype, or architecture at all? Because as you show us, in these pavilions, virtual and real are interwoven by physical reality. And I think that your examples aren't only a model of architecture, but are an example of a new way for architecture. So I want to know, how do you define them? A model, prototype, or architecture at all?
I think these research pavilions, how we call them, have various different aspects in regards to our work. I would say they are, on the one hand, proto-architectural, in the sense that they foreground a certain aspect that does maybe not engage with the kind of full scope of social and cultural complexity that architecture usually deal with. On the other hand, I don't know about another architectural typology that was so productive than the pavilion is. So I'm also tempted to think about it as architecture at the same time. And I think the fact that it's temporary may actually be a good, first of all, one of the Landesgartenschau exhibition hall that I showed is not a temporary building, that's a permanent building. But that may not even matter. But I think we have learned in the history of the 20th century, where the pavilion was really the vehicle for exploration, that some of the kind of, and I said in all modesty because I don't want to give these pavilions that status, but I think generally the pavilion has been the driver for innovation architecture. That's why we tend to sort of pavilions that have been built in Barcelona and knocked down after half a year or a year have been rebuilt 60 years later because somebody recognized, oh, that may have been more influential than all the other stuff that was there the last 60 years for the way we conceive of architecture as an offspring of that Barcelona pavilion as a starting point. So I think the relevance for architecture may not necessarily be judged by the kind of duration that a material object resides on site. So, don't know whether that answered your question, but your question was a question and a comment at the same time, so I think we're kind of on the same line.
I liked a lot the experience on the carcass of the lobster. It's, because I think in nature there is all the answers. Evolution is better than has the answers. So to architects come to and to see the layers of the lobster and to through tar verify to do architecture. I guess it's like they do for planes. They see the bees how they should be taught in a different way and in universities and because it's very interdisciplinary with biology and mechanics. So architecture should be taught in a different way.
Here's a question. Okay. First of all, I greatly appreciate your enthusiasm. I may need to add that I have a slightly different view on evolution, because one of the mind-boggling things about evolution is it doesn't provide answers. It's because there's no question. So I think very often also we have this engineering thought that evolution optimizes stuff, but if there's no goal, there's also no optimization. It just happens, you know. Unless you are a creationist, then maybe a different story. But so I think that's the first thing that you need to kind of understand, no? And I think what is obviously there are certain things that evolve that turn out to be relatively good in the particular context in which they operate. But I think for me the most interesting thing about looking at natural systems is not that necessarily they do things that are superior to technical things. It's just that they do things very, very different, that nature does things very, very differently. Very often in a very counterintuitive manner. No? Use the same material, but use it in a sort of functionally graded form. It's kind of, usually in technology we do exactly the opposite. Have different functions, use different materials. And that's kind of, that applies to almost all kinds of precedents that we have in technology, that if you engage with how nature does things, they're not necessarily better, but they're very different. And because nature, there's one constant in nature, which is kind of the scarcity of the resources. As we more and more venture into a world where the scarcity of resources will become a determining factor for whatever we do, nature may also not be the worst model to look at when it comes to finding alternative ideas. But I think I think it's more about the kind of challenging your preconceptions of how things are done rather than finding an optimal way for doing things.
I was talking about evolution because optimum would be evolution. So the lobster doesn't need more material on his back, so evolution led him to this shape.
Yeah, but evolution doesn't stop, and it may turn into something else tomorrow because there's no goal. I mean, the concept of optimization requires a goal. Nature has no goal. Or if you yeah, but survival is a kind of sort of at that very moment in time. That's not a goal to evolve towards. It's kind of a snapshot in time. And it's always in a high level of interdependencies. So I think it's more a model for, evolution is very interesting as an explorative process. It's not so interesting as an optimization process. That's a kind of superimposition of engineering thinking of how evolution may work, which biologists totally disagree with, actually. The second part of the question is, I do agree that we can learn a lot, actually, just in that challenging of preconceptions of how architects think, when we start to not only assume what biology does, but when we actually get biologists to talk about how biology does things. So I think it's a very valuable model to have a multidisciplinary design culture. And that's what we do in Stuttgart, where in our master course we have architects, engineers, and natural scientists working side by side together, actually, on eye level, not the architect expecting the biology to be just a service provider for coming up with some nice ideas. That's also important.
Any questions? The professors don't want to say anything about the lecture?
I have a question for both. In reality, I have to say that I think that modernist architecture is dead, so we have to find a new way to revitalize our very aristocratic idea of Italian architecture. So I enjoy a lot your lecture, but as an old architect, I have some problem every time. And so just a little feedback. For my discipline, that is starting the Renaissance, when we have to start to think about an object, we have to think about something that is, according to Alberti, sine ulla materia. So it's an idea. So my question is about what does it mean invention? Because if I have to start sine ulla materia, so it's an idea, nowadays, after your lecture, it seems to me that I have to change my way of thinking because through the material, I have to try to invent the new rule of performance capacity to explore environment. So for me, it's quite difficult because I have to change my way of thinking about it. And that is so much difficult because for me, virtual is not unreal. Virtual is mental. So the opposite of virtual is not real, but is corporeal. So mental could be also real. And imagination is something that sometimes is so real that I could design it and drawing it and produce a model. So it's absolutely different. You start from the affordances of the material and you are able to produce a form. So what does it mean if the nature is a deposit of imagination, imaginary? What does it mean invention for an architect? Because my point is not my point, is a quote, but it seems that nature, in everything in the nature is determined. But if I think about the color of a butterfly, it seems to me that also in the nature there is something that I couldn't conceive. And I need an invention, an inventive system to be able to catch something that is not in the material, that is in my brain. Sometimes I think about the drawing of the Cappella Sistina that is a god represented as a section of the human brain. And I think that it's so powerful. So God is in my brain. So how I could say that I could invent something for my era and to pass some values to my daughters, to my children.
Is okay? Yeah. Well, thanks. Also, what an overview, no? So many rich ideas in it. I see I'm gonna, maybe it's a bit long, so if the answer, no? But if it's too long, just stop me, okay? Exactly, I also have to go to the airport, which is also, okay, so the first thing is that I see the role of computer and computation as prosthetics, as a way of augment, my imagination, my ability. I think this Sanford Quinter quote is excellent. Also, Sanford Quinter is one of those that remind us that the computer is first of all material and only after something else. So the role of computation in the work is an augmentation, as a prosthetics, not unlike my glasses, let's say. That's one. The second thing is that Alberti. If you look at the work on the last project, which I know I went through a bit kind of quickly, that is very much the work that I'm working on at the moment. And there's another project which is not here, which is okay, in which we work with a neuroanatomist in order to rethink the way in which we represent space. And one of the first kind of basic axioms that we make for that research is that Albertian understanding of space is no longer relevant. And what that comes to replace with that is an idea that actually, and this is a problem that is actually inbuilt in most CAD packages, that most CAD packages operate on threshold boundaries and therefore in division of things. But that is an abstraction that actually doesn't find a kind of a translation into reality. There's not such a thing that the experiential world is one of continuity. And why then neuroanatomy is interesting? Because we all know that how they see the brain is very much based on an idea, or not only an idea, but actually a capacity to see the brain as a continuum. No? That's when you get your brain scanned with an MRI, you go into a voxel space, okay, may be made out of cubes, but they're all placeholders. Actually, it's a continuum space. And I think it's not by chance that we go towards neuroanatomy, because also that idea of the brain is gone. The brain is an organ of the human body, which is here, we know that, but different from the brain is the mind, and the mind is not so clear where it is. Where the mind can be found is not clear. And again, I'm just quoting Bateson when he says, what happens to the blind stick, no? Where is the eye of a blind person when he or she uses a stick to walk? And he claims that, of course, it's at the tip of the stick. And therefore, again, just to reiterate the point, you see there that kind of a prosthetics enhances, blurs, shifts the boundary between, let's say, the self and the environment. Right, I have a plane to catch. So.
Also got a plane to catch, but and if you get, yeah, okay. But I think it's a very relevant question, because I think that's at, you put your finger at the heart of, let's say, I guess the argument that the two of us tried to make. And I think in my case, I would say Alberti sort of invented the modern designer by actually postulating that there needs to be a division between the intellectual activity of design and the physical process of making. And by that, and that was actually sort of enabled by the sort of advances in projective geometry at the same time. And from then on, we have experienced 500 years of the primacy of geometry or projective techniques, which have preconditioned our design thinking to such a degree that we actually think in geometry. No? And our notational systems of how we design have become also the instructions for how we actually pass on that information to the execution of the building. And what I'm basically trying to imagine is that this process is now, this era, which is 500 years old, is coming to an end. And we can use the computer in a much better way than a drawing machine, which I think is really, the computer is quite bad at. It's also quite a sort of bad visualization machine, but it's a very good computing machine. So why don't we use the computer to compute to enable us to do things that we could not do before because our way of thinking was determined by our kind of giving sort of implicit hierarchy of always prioritizing geometry over, for example, the processes of materialization. So I think that's when the computer becomes the kind of interface to the physical rather than the divider. And I think it's a crucial difference. Regards to the kind of comment you made about nature, I may take up your example. And again, it's sort of interesting to see that a butterfly wing has actually no color. If you zoom in, it's all black. It's kind of the refractive structuring of the surface that creates the color in your eye. No? So it's not our common understanding that there is a colored surface. The surface of a butterfly wing actually produces the effect of color in a totally different way that we usually think about it. I think that's where nature is really interesting. Sort of, it's kind of showcasing very different ways of going about things by taking maximum advantage of the very materiality of things. And I think they only become accessible once we have overcome this kind of hierarchy of always prioritizing the generation of form and then thinking about materialization or construction, fabrication, however you may call it in architecture, as the step that only is kind of goes from sort of imagination to realization. I think materialization is probably one of the most creative processes that we can engage with. And because in nature, materialization and form generation is never separate. It's always happening at the same time. I think it's at least an interesting sort of experimental venture to pursue that for a moment also as architects. That's and because we now have the technologies that actually allow us to do this. And I think this is really a profound change. The computer is definitely not just the next or another tool. It's actually really a challenge to our understanding of the world, I would say.
I have a curiosity for you, maybe especially for Achim, because I think that often technologies, also way of drawing, of representing architecture, techniques, are a narrow connection with the form of buildings. It's not, of course, not all of the concrete buildings are the same. You can make many different things with concrete, but concrete changed architecture. The same for steel, the same for timber, etc. Now, the kind of technologies and also of digital techniques that you are using to make architecture, I have the impression that maybe, I don't know if it's correct, but I have the impression that generate a specific kind of architecture. It's an architecture that seems to me pavilionaire in a way. It's a light architecture, is an architecture that is never serial, has no seriality. Everything can be different because it's a digital construct. So is organic, for example. Is architectural buildings that is difficult to close because are open structures or are light structures. So there is a relationship between the technologies and the architectural form. But this for me is quite evident. It's not precise, it can change tomorrow, but there is a cloud of buildings that in some way correspond to those kind of techniques. What is interesting for me is that this mutation of these architectural mutations are also social mutations, no? Because prefabrication generated a different kind of making cities, of living, etc. And this for all the techniques. So this kind of architecture, for example, Mario Carpo wrote something about this topic, but for me it's very open, it's very uncertain, but very interesting, because like was for Buckminster Fuller or for Fraiotto that you quoted before, architecture that in some way think about a new kind of society, a new kind of human relationship, a new condition, lifestyle. So this is very interesting for me, but it's also very unclear. I don't know what kind of new life you are promising us, because the explanation often are very technique at the end. But I think that behind that there is the possibility of imagining different human relationship, different working relationship, different way to stay together, etc. A new society.
Sure. Well, I think, I will not answer the question of form and material because obviously it falls more. But there is, yes, I really hope that all this effort changes the way we behave. I will not try to say that these technologies are inherently more democratic and all that kind of stuff, which is, I think, daily evidence proves that the opposite is more often the truth. But one interesting thing that I think is possible and it's required is our ability to operate at scale and time span that are, let's say, hard to access for humans. No? And we know that we know that our planet is tipping over the edge, beyond which it won't be possible to sort of maintain the climatic system within a certain equilibrium. And that problem itself has, I think, relationships to design in the shape of understanding larger scale and larger time frame. Now, some of the projects that I was showing begin to, in no way answer any of these questions comprehensively, but begin to try to understand that tool and its interface with reality begins to allow us to have models for engaging with that level of complexity. And I think that is a political problem and therefore is a design problem.
I think that's a very, very interesting and very relevant question because I would say to a certain degree it's probably an engagement that is with technology that doesn't have necessarily a given goal in terms of having a kind of moral insistence on how society should be, but it's actually more understood from that we cannot go on as we do right now. Both from the perspective that these technologies are not necessarily inherently good, so to say, that we should be aware of how we can actually turn them and utilize them to our best, but I think it's also that simply the perception of, at least I would say, my generation of architects is that we recognize, the way we deal with these overwhelming problems that actually the built environment creates with 60% of the energy consumption. I mean, all these things that incremental improvement will not get us there. No, we can. And I think in Germany, we're very good at trying to hope that squeezing another % of efficiency out of the wall insulation will actually save the world, but it won't. At one point, one needs to start to do the radical rethinking. And while the radical rethinking always has this tendency to be slightly on the naive side, or on the uninformed side when it starts off, and cannot showcase necessarily the results, I think it's something that in this kind of situation that you nicely described is something that needs to take place. I would by no means claim that what we're trying to do is on the right track, but I think you need to launch 10 tracks to have the chance that one radical way of rethinking of how we do things will ultimately be successful. Because just trying to incrementally improve the way we go about things is, as we see, too slow and will not get us there. No? So I think that's sort of more the very underlying ambition in the work that we really need to go and challenge our most profound preconceptions because otherwise we run the risk to fundamentally destroy the planet for good. No?
Okay, if there is no more questions, thank you to our lecturers, to Achim, Roberto, thank you to Antonella, Contin, and Ingrid Paoletti who invited you, and thank you to everybody for the attention. The conference, the lectures of Miaw go on next week, starting on Monday with Carlos Ciencio Vandosel, and then the other appointments that you can find on the blog. Thank you very much.